start. So we'll have the last lecture indeed. I will continue discussing dispersion relations, and we will discuss, is it okay?
Yeah, sorry.
A few of the methods that people have been exploring. So maybe it will not be very detailed, but you will hopefully get some idea of what people have been doing. So remember last time we ended up with dispersion relations, and we were thinking about them as IR plus UV equals to 0. So IR we can think of in terms of some low energy expansion, and UV is a statement about the high energies where we will use the basic principles. So last time we derived the bound on the growth, on the local growth of the amplitude, which is something which is different from the Froissart bound. Remember always the Froissart bound is a statement about asymptotic growth. But there is also this bound on the local growth that we derived last time. And today we focus on yet another question. So Froissart bound is really asymptotic. Last lecture we discussed a little bit less energy, but it can be large. And today we focus on low energy expansion of the amplitude. So let's start with this term, IR. And well, IR usually you can think of writing some effective field theory, some Lagrangian maybe with you know, Wilson coefficients, high derivative operators, etc. But I will consider for simplicity the expansion of, well, you can think of ST and U for this purpose being small. So let's imagine, you can imagine something like this. Remember S plus T plus U form squared. So this is something that comes, say, from, if you have in the Lagrangian phi cube, you will get this type of diagrams with here S minus M squared. So here I consider the fact that massless exchange. It is not so important. Then we have some coupling G naught. This corresponds to phi to the fourth in the Lagrangian, etc. You can continue. So, for example, you can consider this coupling 2 s squared plus t squared plus u squared. So this corresponds to g phi to the fourth, etc., etc., etc. So let me just write it. Like this. So, two comments about this formula. First, you see the principle. The principle here is that I consider the amplitude which is fully crossing symmetric. If you remember, crossing symmetry allowed us to analytically continue between different regions, but also we can shuffle different variables, and this is true for scattering of identical particles. So here you see all the terms are manifested fully crossing symmetry. So this is the first comment. So here in this expression, crossing symmetry is manifest. And the second comment is that here is you can ask, how do I know that the expansion is a polynomial expansion like that? And in fact, in general, it doesn't have to be. And if you have a loops of massless particles, there will be logs. So there could be things like log S, log T, log U. And so all these things, for the moment, let me imagine that loops of massless particles are suppressed. Somehow there is a small parameter that suppresses them, so I can neglect them. It is a bit subtle when you actually can do that, and we can discuss that, but it's common and has been common in the last year to consider this kind of expansion, and this is sometimes called tree-level EFT. In fact, I don't know, maybe someone calls it like that, but let's call it tree-level EFT. By tree-level, I mean that there are no logs here in this expansion. Again, we are expanding here for small st and u, so you can think of st and u being all small. They are, of course, dimensional parameters, so these couplings have different dimensions, but you see I arrange them as we have 1 over s, constant, square, cube, etc. And the idea is that, let's say you have your theory, maybe it's renormalizable theory, so you measured your theory like that, but let's say you have some, in general, you expect the theory has an upper cutoff and you expect to have high derivative operators, but these high derivative operators have not been measured in the experiment, so you maybe would like to cook up some model which has these high derivative operators. And here we would like to understand what is the structure of these high derivative operators based on consistency. So if you then have your model, well, let's say we derive some bounds, and then you cook up some model, and it violates the bounds, then it would mean that you cannot use it completely in some unitary way. So if you believe in the basic axioms, you would say this model is ruled out. So that's the idea. Now, to proceed with this, let's write dispersion relations, the one we discussed yesterday. And remember, we had subtractions. So let me choose the subtraction constant S1 to be 0 and S2 to be minus T. Maybe it's a little exercise, but you can check that if you do that, the dispersion relations takes the form that the amplitude is equal plus f naught t, which was related to evaluating the amplitude at some point, plus s 1 of t plus c s scale to develop the discontinuity. And if you remember, this was just when we were applying, when we were deriving these relations, we use essentially a Cauchy argument. So we use analytic properties of the amplitude, and we use that it's polynomially bounded, which allowed us to drop the term at infinity. And more generally, when you hear the words dispersion relations, it's always a statement about when you write the amplitude schematically as the integral of a disk of an amplitude. This is what it is. And now here the first things that we can learn. So again, this couplings G, you can relate them to couplings in your Lagrangian. However, in your Lagrangian you can do field redefinitions, so it might be sometimes ambiguous which couplings correspond to which terms, whereas the amplitude is physically observable, so let me call this different coefficient G Wilson coefficients. So the first question that I can ask is which Wilson coefficients admit a representation, dispersive representation. And what does it mean to admit a dispersive representation? By the analogy with amplitude, coupling definition. So Wilson coefficient G is dispersive if we can write it as G is an integral of a discontinuity of the. So if you can write your Wilson coefficient as a discontinuity amplitude, I will call the coupling dispersive. So the first thing we're learning now is that starting from a relativistic quantum field theory, we try to argue in the course that you have this polynomial behavior at infinity with power 2. In fact, let me say it without proving, but for gravitational theories, it's the same behavior. Effectively, you also have this power 2. So there is no distinction at this point, much distinction between gravity and QFT. And what we see is that some couplings here are dispersive and some are not. For example, this coupling G square is clearly not dispersive because it does not, we cannot write it. If I plug now the expansion of T here, these terms will just cancel. So this is non-dispersive coupling. So let me write non-dispersive. It's this G squared. Now let's look at the next term, G naught. Well, G naught is also non-dispersive because it will require a contribution from F naught. F naught can have a constant in its expansion. F naught, it's a function of T. So imagine we expand it at small t and it has some constant, then G naught will be equal to this constant plus the discontinuity. So this does not satisfy this. It should be purely integral of discontinuity by definition. So G naught is also not dispersive. And that's it. Everything else is dispersive. Because you see, let's take, for example, G squared. It has a contribution which starts from S squared. So these two terms will not contribute. If we differentiate this, let's say we subtract this, we differentiate twice with S, with respect to S. These two terms die, and so we will get a formula G2 equal to the integral of discontinuity. So all other couplings are dispersive. So something interesting here to note is that, in fact, this maybe from the experimental point of view, these are couplings maybe the most important, the most interesting. And you want to understand their structure from the UV. And at the level of this dispersion relation, I cannot say anything. These are really parameters that you measure in the experiment. They're non-dispersive. And since it's integral from discontinuity, you can think of this as the integral from the M gap to infinity. So this is a UV. So non-dispersive, meaning not being expressible in terms of some UV physics. Okay. So what can we do with dispersive couplings? Let me tell you the most famous result in this subject. I have to say, one of the very famous result, which maybe was discussed 10 years ago. And then I'll switch to the recent progress. It's the following fact. Let me define the following couplings, and then we can relate it to this couplings G. So I define in this couplings mu as follows. 1/2 factorial. We take 2n derivatives from the amplitude t. Let me subtract this massless poles from this amplitude. So let me move this to the left. Right here plus, right here equality. And let me call this t plus this massless poles t10. So then we take the 2n's derivative of t hat, and let me set t equals u, t equals to 0, sorry. T equals s equals to 0. So what we do is now we take this formula, we takes two n derivatives, n will be here larger equals than 1, so when n equals 1, you have two derivatives, so these terms never contribute. And so all these mu n's are dispersive couplings. And you get the formula which looks like that. So here, all these terms, you see t equals 0, so you have this s prime, and here t equals 0, it also gives you s prime. So in total, you get this to n minus 1. Now, the point here is that, okay, this is just a fact, something we derive from dispersion relations. But the important point is that this function Ts is non-negative. And so, in general, when we talk about bootstrap, any kind of bootstrap positivity is always a very important property. And so remember that we had the partial wave expansion for this guy. Here's the Legendre polynomial, which we evaluated 0, which is the same as it evaluated at 1. So all these guys are equal to 1. These are non-negative. So Ts of 0 equal, they're all positive. So you see that if we think of this as some averaging with a non-negative density, we get that all these mu n's differ. It's an integral of the same non-negative density with different powers. So this is an example of what is known as a moment problem, which is a, I believe, 19th century problem in physics or in mathematics. Anyhow, it was solved a long time ago. And the moment problem is the following problem. And I will talk about briefly about what's known as a Hausdorff 1D moment problem. So what is a moment problem? Imagine someone gives you a set of numbers. This is a set of numbers. Someone gives it to you. And the question is, can you write this set of numbers as the integral from 0 to 1 and of some, say, positive density, like we had here, times x to the n. So that's a question. And for this particular case, this problem has been completely solved, and this integral from 0 to 1 is, you see, if you switch from this variable s prime to the variable m gap square over x, then this x goes from 0 to 1. So these moment problems are really ubiquitous in physics. They're really everywhere. And the reason is that because of unitarity, we often encounter this sort of positive densities, which effectively are some sort of total cross sections. So, therefore, it's good to learn a little bit about them. And so for this case, the solution is trivial. The statement is that this set of numbers comes from some non-negative. This is a crucial non-negative spectrum. positive density, you can think of this as the distribution of mass. If and only if these moments satisfy the following condition. Where delta mu n is defined as a shifting operator. It's n plus 1 minus n. So you take all kinds of shifts, and all these things has to be positive. So let me just briefly check that it's indeed the case, so that it's not a mystery for you. So going from showing in one direction, let's say you're given a non-negative rho, how do you show that this is positive? Well, this is easy. You show, it just follows from the fact that this thing, you can check, it's nothing but 0, 1, 0, x, and x to the n, 1 minus x to the k. And so clearly, this integrand is non-negative, this is non-negative, so this is positive. So one direction is easy. Now another direction, which is converse, is a bit more complicated. Namely, let's say you know that all these moments are positive. How do you show that this rho of x is also non-negative? And here you can use the following trick, is that you recall that these guys are effectively what is known as the Bernstein polynomials. And then you can use what's known as the Weierstrass theorem, which says that if you have a continuous function between 0 and 1, you can approximate it with arbitrary precision with polynomials, and in fact Bernstein polynomials is a complete basis of polynomials. So then you can pick any very sharp function localized at some x, build it out of Bernstein polynomials, and then you know the integral is positive, so therefore this 0x is positive. So that's the idea. Let's just write some simple type of bounds that you get. For example, let's say you know in your experiment you can measure 0, 1, and 2. Right, let's say you can measure these bounds. Well, what do you know? One thing you know is that m0 is larger than or equals than m1, larger than or equals than m2. Right, this you know because you're integrating something non-negative against the power of x between 0 and 1, and adding more powers can only make it less. So this is something easy. Another thing you can consider is that, well, let's say you take the integral of this type, 0x. So this is clearly non-negative, because 1 minus x squared is also non-negative. So if you open this brackets, you see that n0 plus n2 minus 2n1 is also positive. And also you can start with the following thing. Let's say you start with the following combination. n0 times m2 minus mu1 squared. Let me write it like this: dx 0x n0 and 1. This is m0. 0, 1, 0, y with mu2, so y squared. And let me write this mu1 as the integral 0x 0, 1, 0, 1, 0, y. Now notice that this thing, and here of course I put x and y. This is because it's mu1. Now in fact here you see that because of the symmetry between x and y, you can write y squared, or you can equally write y squared plus x squared times 1/2. And this is because, well, these terms are equal to each other. So times 2 you get back the same thing. And so we see that this combination is equal to 0, 1, 0x, 0, y, x minus y squared is also non-negative. And in fact, these are the all conditions you have on these moments if you don't know any other moments. But what I want to tell you here is just that when you study dispersion relations, moment problem immediately arises. And these couplings, if you wish, if we plot them now, let's say we define some ratios, and we plot all these constraints on the plane, we will find some geometry. And well, this geometry expresses this positivity. And in case of one-dimensional moment problem, well, we can just take these three numbers, plot everything, and understand everything. And yeah, there is a nice paper which explored this last year by Francesco Riva and collaborators. So if you want, you can take a look at it there. But this one-dimensional moment problem is something which we already saw sort of many years ago. So what's the new development from the last year? So the new development is the following. You see that here, what I have done in defining these moments, we set t equal to 0, and so this t dependence was effectively lost. We would just set t equal to 0, and we differentiate with respect to s many times, and we recover this moment problem. What if we don't do that? So if you don't do that, the following structure emerges. Well, we still have these dispersion relations, but then the discontinuity which enters here, let me not erase it, it has the following structure. So the discontinuity is, if you remember again, there's some extension on this side. Here I'm taking the particles to be massless, that's why there is no more 4m squared here. So what's the difference compared to this formula? Well, the difference compared to this formula is that instead of this PJ of 1, we now have this dependence. And you see that if we try to expand this Legendre polynomial, before we just took it at t equals 0, let's not do it, let's just expand it around t equals 0. So we get the following formula. It's just a fact about these d-dimensional Legendre polynomials. The dot, where this it's supposed to be calligraphic j squared. It is different from this j, and calligraphic j squared is a quadratic Casimir of rotation group in d dimensions. It's this. So you see that as we expand, if we expand this function in small t, we naturally start getting these powers of j. instead of just having this sum, well, we have this sum to leading order, then we have j square, and all these j's are, again, some positive things. Therefore, it's natural to define the following moment, two-dimensional moments. So, what are these rho j's? Well, these rho j's are related to this imaginary part of j, so they are non-negative. Now, this j square are just this j square, and these moments of m and n that are defined here, you can check that they're related in some simple or in some computable way to the Wilson coefficients. Because let's say we have this expansion for small s and t. Let's say we do that expansion, then we can match the Wilson coefficients that appear in this expansion to this mu of n. So it's just a different choice of couplings. But we see that in the scattering amplitudes, for relativistic scattering amplitudes in relativistic QFT, Wilson coefficients form naturally a solution to 2D moment problem. 2D because now we have two variables, j, which is discrete, and rho, which is integral over s. So this 2D moment problem somehow, and again, as before, we saw that there is some set of constraints. We can explore the set of constraints and derive some bounds on Wilson coefficients. So this 2D moment problem has not been explored until last year for some reason. And you can explore the solutions to this 2D moment problem. And it has different yes, first of all, it's in general 2D moment problems in math, they're much more complicated. So if you ask what is the set of necessary and sufficient conditions for a certain set of numbers, this mu m and n to be representable as this 2D solutions, I think in some cases they're known. I don't know, Francesco, is there even general theorem, which is necessary and sufficient?
Yeah, you have an infinite set. You can have an infinite set of conditions
Yes.
that give you the thing. But and as you say, under certain conditions, there exist, and if these are not satisfied, you don't even have.
So yeah, mathematicians figure it out, and there is a set of conditions which you have to check. But let's say if you know just a few of them, it's a much more complicated task. Before, I just told you that, in fact, if you know 3 moments for 1D moment problem, this is all you have. If you know 3 of those, it's not clear. So this is an open problem already. And yeah, this kind of structure, which appears in the space of Wilson coefficients, was eftihedron. I guess referring to the geometry that appears underlying this set of constraints. You can also hear that, okay, well, let me just stop it here. So this is what is known as the eftihedron. It's just a statement that if you start with dispersion relations and you study their expansion at low energies, you have this 2D moment problem, and there is a certain geometry that emerges. And then it's a task, what you can say about this geometry, blah, blah, blah. And, yeah, you can find this analysis for some particular examples of couplings in the recent papers. But The basic thing is that we have this bounce.
Sorry, yes, the rho j that you wrote, is that expressed in terms of the imaginary part of the fj's, or
Exactly.
exactly that, or
it's just that times maybe mj.
Yeah,
Maybe
yeah,
times
thanks.
this. But the dynamical information is this.
Yeah.
So you see here we are using a little bit more already, and if we use a little bit more, well, we will get a better bounce. So this is already an improvement on top of what we achieved before, but there isn't one more constraint which we haven't used, and this relies on some fundamental property of the dispersion relations.
Sorry.
Yes.
This positivity property of the Gegenbauer or the John function, is it really just a fact of life? Is there some unitarity reason for it? I mean, is that not lucky?
I don't have a good explanation for that. Neither I've seen it in the literature. In fact, in this iptychedron paper, in the original one, it was presented a bit of a miracle. If you start taking Legendre polynomials, you start differentiating them around x equals 0, you start building various matrices around it. You find there are zillions conditions, there is whatever, some cyclic polytope. So somehow Legendre polynomials, there is some geometry underlying them.
Sasha, if I can say something,
yeah.
In fact, you don't really care that this expansion in the second line up there, it's positive.
Yes, that's what exactly that I was going to say. But the way I'm presenting now is very different. Is that forget about these mysterious things. Here I just expand that, and I collect all these moments, and I define this moment with a plus sign. So even if you change a sign here with a minus, I just define sign, I define the moments, and what will change is the relation between μ's and the Wilson coefficients. So this geometry is there, based on just the fact that the spin is there. But you're right, maybe Legendres do have some magic properties, and I think people explored a bit this manifestation in the space of couplings. But the structure of the 2D moment problem is just the statement that Legendre polynomials admitted polynomial expansion in J.
So in fact, I completely misunderstood this. The sign in front of the x is completely irrelevant.
Yeah. It's you can flip it. I can still define these moments, and.
But would there be that going from Newton to the Wilson coefficients, then if you go through Newton-Wilson coefficient, then if there are too many signs, maybe you lose all the bounds, and it's also possible.
Yes, exactly. So if there is, by flipping the signs, there will be connection with Wilson coefficients, and I don't know how it will get affected. Okay, so
Part of the point is that these μ's are bounded from below and above. So independently whether there's a minus sign in front, it's still a clone.
There's always a return. Yeah.
So we are not yet there, I think. They are not yet bounded from two sides. I think you think it's enough?
No.
Yeah. So one thing which is we're coming there. So which is you can see from here is that the bounds of the type. Okay, well, μ2 is larger than μ1, and larger than μ1 squared, but μ2 is not bounded, say, from above one. So these coefficients, we have a one-sided bounce, and what will happen now is okay. Let's continue. So far, the punchline which I want you to take away from here, maybe even from this course, practically, is that we discuss the basic principles, analyticity, unitarity, and crossing. We use them to write down dispersion relations, and now we discovered that all the structure generates a two-dimensional moment problem. This is true in quantum field theory, this is true in gravity, on the very general grounds. So this is our understanding of effective field theory from the sort of S matrix bootstrap today. Now, there is one extra fundamental property of dispersion relation which we haven't discussed. What is that? This is the following fact, is that, let me remind you again, write down again the formula for the dispersion relations. And if you remember, there was a term which looks like this, with a discontinuity. Now notice the following fact, that if I look at this discontinuity and I ask about the crossing, then this crossing relation is there. Indeed, let's just check it. So what is U for the massless? To check this relation, we just switch S to U in this. Well, U is minus S minus T. So S goes to minus S minus T. S goes to minus S minus T. This becomes minus S. This goes to itself. This just depends on T. This is not affected. And this is invariant. So crossing dispersion relation are manifestly crossing symmetric under this crossing. So this is checked. However, remember, if we have these identical particles, we have another crossing relation. This other crossing relation states that Ts of T is equal to T of S. And as you can see, if you try to do this change, the formula changes. So just look at this formula, switch S and T, you see the formula looks different. It's not crossing symmetric anymore. Therefore, if I write, and remember that this equation was valid. Let me emphasize again that we have this dispersion relation with two subtractions. On T less than 0, say in gravitational theories, or T less than 4m squared in gap theories. So whatever you prefer. Now you see that if I plug for each of these guys this equation, and I can also I have to be a little bit more careful, because remember, if I want to have an expression which only depends on the discontinuity, I have to get rid of the subtraction terms. Remember, there were subtraction terms, f0t plus s f1t, and this are not expressed in terms of discontinuity, so I can swap them, and they will be still here, but the way you can get rid of them by taking, for example, let's just take d to s. If we take second derivative with respect to s, these guys are gone, and we take d to t. So this is now a crossing symmetric relation. And if we write it, this will be a condition on the discontinuity. So let's just write this equation. So if we write the left-hand side, we we'll have d to s, d to t, integral ds prime t s s prime t is kernel, which we have here, s prime st. And this should be equal to d to s, d to t, ds prime ts, s prime s, k s prime ts. So this thing we can call this equation. And here the only unknown is this discontinuity of the amplitude, so it's exactly this rho of j, this imaginary part of f. So the real unknown, the dynamical unknown here is sitting here as a sum of j in j as j. So these are the dynamical contents. So this we see that crossing symmetry applied to dispersion relations leads to this set of constraints, and this condition is called, we can call it dispersive crossing. And this is a completely general fact, which yes, and because we use it in one channel for t negative, so when we sweep the channel, it will be s negative. So this dispersive crossing is valid as t negative. So this equation is there, and in principle, we have to learn what's its implications. And this is not what people have done so far. So instead, people chose a simpler path. And the simpler path is related to this condition. Remember, at the very beginning of the lecture, I start writing the low energy expression, and I only kept polynomial terms. I said there is no log s. If you have a massless loop, you will change. If you have a loop of massless particles, something like this, it will generate for you log s. So we assume that these guys are not there, and so then we wrote this expansion. So what people did, in fact, they proceed, let's impose dispersive crossing, again, getting rid of these massless particles. Now, if we want to take into account massless particles, we have to deal with this equation, which okay, I think it hasn't been done. But now let's go back to our simpler problem, which is a tree-level EFT. And then we note the following fact. For example, let's focus on some coupling. We can take something which I called, say, 4G40. This coupling looks like this. And here you see, of course, not only this crossing is manifest, but also this crossing is also manifest. It's fully crossing symmetric. So now we can write two different formulas for G4 naught. This. Just using this. We can write it like this. ds2, dt2, we have st, s equals t equals 0. So you should just check, plug here u equal minus s minus t, differentiate twice with respect to t with respect to s, set st to 0, you will just get G40. Or we can write it like this. That's again, we'll get the same result. You can check. So therefore, we see we have two different representations for the coupling. And now let's evaluate, let's take the difference between these two representations and evaluate it using dispersion relations. And so we get the equation. And again, I chose such that the number of derivatives is high enough to get rid of all the subtraction terms. And so you get the equation. So this is just as I'm saying that there are two ways to express the same coupling, so let me take the difference between the two, it has to be 0. As dispersive crossing, it's an expression of this crossing symmetry. And so dispersive crossing applied to the tree-level AFTs. So this was important. You remember that it was important that we assume that there is this expansion leads to what is known as null constraints. This is just a name, which was, again, out in one of the papers. So this is an example of a null constraint. However, just I want to make it clear, so again, dispersion relations have two channels. One crossing is manifest, one is not. You can write a different crossing, you get some equation, and if you write this equation applied to tree-level AFTs, this is called null constraint. Yes?
Sorry, superficially it doesn't look, I mean, I understand that it's the same content, but superficially it doesn't look like the same equation, right? Above you have, on the right-hand side, the second argument is S, so there is really T, the discontinuity in the S channel evaluated at S, instead here there isn't. So is it really just you can plug in there and obtain the same? So why didn't we start from that equation and instead we use the trick of starting from the crossing symmetry amplitude?
Why didn't we start from there?
Yeah, directly. Because here it doesn't look like it's the same expression as above, at least superficially.
Well, yes, I agree. I agree. This is not the same. Here we're expanding everything around s equals t equals 0.
Yeah.
So we can try, if we expand again, this will be just evaluated around 0 and its derivatives. If we expanded both things around 0, it will also be evaluated around 0. So there is a chance. But the point is that here, yeah, this equation is always valid because I just derived it from dispersion relations, but here I made extra assumptions, which is that I can expand the amplitude around 0.
Yeah, but so all the null constraints that have been discussed, you can all derive them from that equation, just inserting the discontinuity of the amplitude in terms of the effective field theory. That's the statement. There is nothing else.
I think so. Yeah, I think so.
And then why is it complicated to just do, I don't know, a loop, like you have massless particles, you have the loop, say some derivatively coupled massless particles, so that its effective field theory works. Does this whole thing completely break down?
Well, this thing breaks down, my understanding. I guess Francesco has tried to do it for some time.
Yeah, the thing at the bottom breaks down because now when you take t equal to 0, and this second derivative with respect to t, there are some t square logs of t that goes to infinity. So yeah, the last line does not survive.
Yeah, but this line is fine. However, I think we just haven't explored it yet. Okay, let me make. So at this point, yes, I would like now to come back to Francesco's comment. which is that. So what do you get now? Let's say you take all these null constraints and you apply them to tree-level EFTs. What do you get? Well, one way people formulate it again. So this is due to this paper by Simon Caron-Elot and Vincent Van Duon last year, and Andrew Tolley and his collaborators, which I don't remember. Now, the punchline, if you now combine all this geometry together, you see that these Wilson coefficients that appear in the EFT, they first bounded, there are two-sided bounds. Or one way, I guess one motto you can use is that, and is dimensional analysis follows from general principles. What do I mean by this? Well, I mean by this, let's say you have Wilson coefficients and you say my theory has some scale where new physics starts, some lambda. Then I guess an effective field theorist will think, okay, well, I have an expansion which is organized by 1 powers 1 over lambda, and there is some coefficients which appear in front, and this coefficient should be of order 1. Just some kind of naturalness expectation. Let's say you integrate out, let's say you have some heavy particles, some heavy propagator, you exchange a heavy particle, well, you can expand it and you will get an expansion with all the coefficients being 1. And the result of this analysis is that this intuition is correct. Indeed, you can prove rigorously, though not just mumbling, but it just follows from general principles that all these couplings, they indeed bounded from two sides and they are order 1. So I think this is a basic QFT fact that this happens in these completions, and then people have been studying the structure of these bounds and where different theories live, and there is some interesting structure, but I will leave it like that.
Can I ask about this? So aren't there some low, at least some low-dimensional couplings or some couplings that are still not bounded two sides? For instance, the coupling of T5 to the fourth, is it bounded by two sides, or it's
Yes, you're right. One has to be careful. There are still some couplings which are not two-sided bound. So say I think T5 to the fourth is bounded from below, but I think from above it might not be bounded. I don't.
And is there a physical reason why these couplings are special and should escape dimensional analysis, or it's just that we're not good enough?
Somehow I think all the high dimensional ones, they are two-sided bounded. Now there are a few special, say D5 to the 4 is but even D5 to the 4, okay, maybe you can check quickly if it's two-sided bounded, but I don't remember now. Yeah.
No, it's not. It's only positive.
Well, in fact, it's not even positive, right? In the gravitational theory,
Yeah,
it can dip. So yes, okay. Let me just put here some little star that you should be more modular, some subtleties, and again. Remember that we started by saying all the couplings can be divided into class, dispersive and non-dispersive, and this is only applies to dispersive couplings. If your coupling is non-dispersive, then just we cannot say anything. So now, yeah, let's take a break. Let's take a break.
Okay, good. Let's take a 10 minutes break. If you by chance have questions, you can speak aloud, we can hear you. Otherwise, good night. somehow with the moments I meant that we got the mu's. And of all those, you have the 0, 1, whatever. And so on, right? So these are already, these are two-sided bounded. All of these guys have already these two-sided bounds.
That's right. Yeah.
This is instead is free. And without constraints, you have the same for all the other guys, right? And then you have this thing that, this direction, I guess they are monotonically in this direction.
Yes.
So in principle, crossing, if you know that one of these is bounded, then there would be enough to, crossing what it does is that it tells you that one of these is equal to one of these, which is bounded, and then everything follows. But alternatively, you could say the mu 0, 50. Actually, it's enough to say that these don't grow super exponential, and then you would find that all of these are also two-sided bounds. Because basically this monotonically increasing, this is Schwartz inequality. You can, if one of these is bounded, because basically you have that mu 100 times the mu 0 is bigger than the mu 1 to the square root of 100. If you see what I mean. If this is finite, then this guy is always finite as well in units of mu 0. Anyway, sorry, I mentioned it because the two-sided bounds structure is already in the moment.
Okay, so you're saying it's not without, without crossing. You're saying it's
well, crossing is necessary to say that one of these is bounded. Is where it enters and but the moment bounds are already giving you this thing. Yeah. So this dispersive cross, how did you call it? Dispersive crossing. Ah, yeah, there it is. Yeah, why? I mean, this can be done directly like this. No? Why is it not as a function? So why don't we do this as a function?
Yeah, we can expand both sides around s equal t equal minus mu.
Yeah, on a finite thing.
And then it will be going.
Yeah, the question is whether you can write the units of this expansion, if you can still write them as moments to insert in the moment problem.
And what about the integrating like Galileo and company style?
Yeah, we can multiply this equation by psi of s, psi of t.
Yeah.
Integrate, and here we go. We have moments which are for some quantities which are
I was a bit confused as to how we know they're bounded from above from the non-constraint that we derive.
Yeah, so I haven't explained that.
Okay.
Yeah, no, I haven't. In fact, it's kind of.
But the case you showed before, the 1D moment problem, you could see the two bounds,
Yes.
right? There you had that mu2 is.
Yeah, okay.
But somehow, what happens that if you use this, if you derive this, if you solve this 2D moment problem, you get say some space of couplings where they're not bounded. But then when you impose crossing, you take effectively a slice of this geometry.
Oh yeah.
And then you find that it's
okay.
Here's one extra condition on this moment. This in the paper by Simone and Rostelli and company. Where, do you remember how they define the null constraints? That they're not defined in this way, but they're defined as contour integrals on this complex T. Is it this? Or no?
good question. Yeah.
Because they are. Maybe the same. I don't know. Now that I see it written by you. because their expression holds also. Well, sorry, no, it's not. Because they have this weird thing of having some evaluated at t equals 0 and some not. Right, sorry, now I remember. That's the difference. You see what I mean? Yeah. So it's not the same. Their contour somehow takes some at 0 and some not. Well, this is truly finite S, finite T for all. Yeah. It's stronger.
Yeah, it's interesting. Let's say we take this thing and we integrate with some size.
Yeah.
And so.
So still, you got a computer and everything? No, you didn't get anything?
No, but I know there are funds for that, no?
There
should be funds.
Yeah, depends on, it's always a debate. You got an iPad?
No, I had it from before. But I am math department, which I think is a bit more, I think they're also a bit more constrained.
Only pen and paper. No, the facility. We are attached to experimental physics here, so next door they buy.
If it's less than a particle accelerator, you can buy it, right?
So
The email I received initially was that in theory that they could offer me a computer, but they would ask very gently if I didn't ask for it.
Please don't ask for a computer. Don't have the money.
Please consider only requesting it if you really need it.
I mean, I don't say no.
the iPad is necessary these days.
Yeah, kind of.
To reduce the waste of paper.
Yeah, I don't know. Actually, if you make the objectively, if you compute the, you know, the ecological impact of your iPad and the paper, I wonder how much time you need to use your iPad for.
But also, it's not producing the paper. The problem. The problem is burning the paper. So actually, if you use it and store it in things, it's CO2 points. I mean, your theoretical physics using paper.
I also buy like this recycled paper for years. I've been doing this. I don't know if it's better.
To me, the iPad is the fact that I'm more willing to do computations with the iPad and paper, and I refine them after some time instead of taking a dirty sheet
full of dust and stuff.
Yeah, I don't know, it's a complicated balance, I know. You can also not produce, there is also a balance in producing paper, right? If you produce too much paper, then you're left without a tree, so there's clearly at some point, I mean, if you should only cut trees that don't grow, then you're not reducing the CO2 storing, but...
What about lithium and whatever crap?
Yeah, exactly.
Yeah. I found a peer-reviewed paper that does a life cycle analysis.
Oh, nice.
Yeah.
And it shows that a paper notebook outperforms tablets in almost all impact categories.
There you go.
So we should fully
Always the
respect.
first one to find things. Exactly, right? You're always, as we discussed, you're always finding the nature, peer-reviewed reference.
That's what we were saying about Gen Z, right? While we're talking, you're on your thing, like looking up.
Right, should we start? Yeah. Sasha will
We'll have to run, yeah?
run in about half an hour. So
That's right.
see you.
See you in some point.
Okay.
Okay, let's now have our final discussion. In the series, so yeah, we discussed dispersion relations, and now we discuss this 2D moment problem and the fact that you have an extra crossing conditions. And then it's you're interested, you should really look up into the papers how it works. But the punchline is that this Wilson coefficients, if you write them down, they live in some shape, which makes them all related to each other and bounded from above and from below with the coefficients of order 1. Now I want to state another cool fact, which is the following: that so far everything in the course we discussed was about the scalar particles. So it could be, say, Higgs boson or pions, but there are of course very interesting particles which have spin, and in particular we have gravitons and photons. And you can ask what happens if we consider instead of scalar particles with spin. Now, I can tell you that analyticity doesn't change. Unitarity changes only slightly. Instead of Legendre polynomials, you have different polynomials. Polynomial boundedness also doesn't change. So, in fact, all these things stay the same. However, there is one effect which is known as sometimes called superconvergence. And again, this is some basic effect about spinning particles. So superconvergence is the following fact: that spin makes couplings dispersive. So the basic intuition, which I will now demonstrate a bit in more detail, is that if your external particles are spinning, you consider the same games that we played, you will find that before we found there are a couple of couplings which are not dispersive, and if you repeat it, say for spinning particles, more couplings become dispersive. So let me consider an example, which is a scattering of gravitons. So gravitons are specified by helicity in 4 dimensions, or projection of their angular momentum in the direction of motion. And if you write, consider, say, 4-point amplitude. Now, as opposed to the scalar case, it depends on the polarization. So let me consider, for example, this amplitude. So you have here, say, I call it plus and minus, and it's some so-called ingoing notations, which means, like, if you consider scattering in the 1, 2 to 3, 4 channels, this describes 1 plus 2 minus into 3 plus 4 minus. So it's an elastic amplitude. And you might have seen that, well, if you have such an amplitude, it is described it depends on polarization of the gravitons, and the dependence on polarization in 4 dimensions is very simple. It's completely fixed, and you have this spinor helicity, so-called spinor helicity variables. But for now, it's just a statement that you consider so polarized gravitons. You have a universal prefactor, which takes care of the fact that these are spinning particles. And then you have a function, which is a function of the Mangosteen invariance. And moreover, you see that if you exchange particles 2 and 3, here, because they're both minus, the process doesn't change. So there is a crossing symmetry relations, which says that F of Q equal Q and S. Now, what is this superconvergence story? Yeah, and let me also write so that you have seen it. If you compute this amplitude in just GR, you will find that this function takes the following form. So, we'll be using here some maybe pi's. That's a result. In three level GR. Now, recall what was our discussion of the analyticity bound. It tells us that the amplitude bounded at infinity, and if you go through the arguments, you find that, in fact, the bound continues to hold. So this, let me take this time t to infinity. Hope you won't get confused. And if you take this amplitude t, plus minus plus, the bound, as before, is that it's less than t squared or negative s. So this is precisely the same as what we had before. However, if you look how this prefactor behaves in the large t limit, you will find that this prefactor behaves like t to the 4th. So the fact that the power is 4th is related to the fact that the spin of the graviton is 2. For example, if you would have photons, you have square here, because each of the spinor helicity carries helicity 1/2, and helicity of the photon is plus or minus 2. So this power is related to helicity, and you see that each helicity factor gives you a power of t. So it tells us that therefore we see that for gravitons, this function of f, in fact, we have that if you take t to infinity, the absolute value of t is f, it's 0 or negative. So by pulling out this prefactor, we gained 4 powers of t. Remember before, for the scalar case, we had the condition that t divided by t squared was 0 in this limit. But now we can multiply by t squared and it's still 0. So this is a phenomenon of superconvergence, that by adding spin to external particles, we have more sum rules. So now we have new sum rules, which were not there before. And the new sum rules look like this. The t, and take t to the n. You take this thing, and you find that this is 0 for n equals 0, 1, and 2. So these sum rules were not there for the in fact, even for n equal -1, it was also not there for the scalar case. So we have this. And the fact that we got 4 is related to the fact that helicity of the graviton is 2. So in fact, we will get 2h new sum rules. So photons, we will have t squared, etc., etc. So in fact, what you find if you write down the sum rules, that in gravity, for scattering of gravitons, all couplings are dispersive. In particular, if you take, say, scattering of Higgs, say Higgs-Higgs scattering, then the Higgs self-coupling is not a dispersive coupling. We cannot express it as something coming from the UV. However, for G Newton, Newton's constant, we can write a formula. G Newton is the integral of the disk of the amplitude. So it's interesting that in some sense, all the power of gravitation is coming from the UV. So this is, so at this point you can ask, okay, now I told you what happens. You see, at this point you already see what the game is. You decide what is the spectrum of the particles in your theory that you have. You decide what you know about them. You write down all the dispersive couplings, and you analyze geometry for all the dispersive couplings. So that's a task of an S-matrix theorist. Now we know what the particles are. We take a standard model plus a graviton. And the question is, what is the geometry that results from that? And this hasn't been done yet. So this is something which hopefully will be done soon, and maybe there is something interesting there. And in particular, you see that by attaching graviton here to the external legs, we can start maybe exploring certain couplings become dispersive. So this is where the subject is. And this is all I wanted to say about the dispersion relations. So, okay. If there are any questions, you can ask them now. So the last part of my story will be, I want to talk about different bootstraps. So, and again, the dispersion relations is something which maybe is important to have in mind, because really we did not assume much beyond what we already know, and so this is really something that can be useful. And in fact, many people working on it coming from different angles. Some work on standard model EFT, some more interested in gravity. So, but in any case, these are all the games we have. We have crossing, analyticity, unitarity, and we try to apply them all. And here I will bring back remember I started my lectures with disclaimers. That first of all, in D equals 4 there are infrared divergences. So how do I deal with that? And the answer is that I don't know yet. So, but the idea is that this technical difficulty, all the same ingredients are still there in 4D. And the second is that we have a cosmological constant. Okay, this I also don't know. We assume that it's somehow that these couplings, these constraints are correct. Even though there is a cosmological constant. But presumably eventually there is a version of the bootstrap which is a 4D de Sitter, where everything is fully understood. But I think this is an intermediate step, and maybe one day we will have a de Sitter bootstrap, and then the flat space will emerge on the limit. It is in fact what happens if you do the bootstrap in ADS in anti-de Sitter space. You take the limit, you just recover all these formulas. You just recover. So it's just different kinematics. Instead of Legendre polynomials, you have Mach polynomials. Otherwise, it's the same. In de Sitter, the problem is that we don't know the rules. Okay, so let me say a few. I will just list results which I think can be useful. And, here. So what are the? Okay, this is one game you can play. What are the different games? So the different games, many of them, you have to be careful. They might depend on extra assumptions. Extra assumption being, for example, extended analyticity. So remember, again, I try to emphasize the more analyticity you have, the more powerful you are. So what do you get if you assume extended analyticity? One famous result, which maybe you would like I would like to say a few words about, is the Froissart-Zhiboedov formula. This formula is an expression of the following fact, which is believed to be true in all theories, in quantum field theory, in gravity, in CFTs, etc. The fact is the following. Before, when we were discussing this fj of s, these partial waves which encode all the information, the j was an took integer values, 0, 1, 2, 3, 4, 5. And a priori, you could have thought that these functions with different spin, they have nothing to do with each other. They just. But again, as it happened before, like we started with two channels, which a priori do have nothing to do with each other. But in fact, there is a canonical analytic continuation which promotes this fj of s into an analytic function of spin. And when spin becomes an integer, you recover the original formula. This phenomenon is called analyticity in spin. So to derive it, it's very easy. It's again similar type of thing, similar to the dispersion relations. Remember, let's start with and importantly, for Froissart-Zhiboedov formula, it uses extended analyticity to beyond what has been proven from the axioms. So let me quickly sketch the derivation. So FGFS is, you can remember and define to take the integral over angles, you take a Legendre polynomial, you take your amplitude, and you just project this partial way. That's the definition. So what happens is that you can rewrite this integral as a contour integral. So even, let's say, we have some integral between -1 and 1. You can rewrite it instead as a contour integral. And the formula that you get is that essentially you get the same formula, but instead of this, you have now a contour integral. Here you have z squared -1, and instead of pj, you have what is known as a qj. So remember that Legendre polynomials satisfy second-order differential equation. So there are two solutions. One is so-called usual Legendre polynomials, the other is a so-called cube Legendre polynomials. And they're related by the fact, so if you take this Q, so-called Q Legendre polynomial, and let's take discontinuity around this cut, as a cut, you get back the Legendre polynomial. That's why this formula works. Now you can try to deform this contour, as we usually do in the dispersion relations. So let's, instead of going here, try to deform, and these cuts which I drew, these are unitarity cuts. And now you can, instead of doing this, deform your contour. Similar to the dispersion relation. And if you're lucky, you can drop this contour at infinity and we get dispersive representation of partial waves. So for our Greenberg formula, it's a dispersive representations for partial waves. And I guess maybe you already now suspect that whenever something becomes dispersive, something good should happen. And it's indeed the case. So if you deform this contour, you get the following representation. You have an integral over this unitary cut, this unitarity cut, and here you have T of t, which means we are taking discontinuity in the t channel. So in fact, this integral here, the z variable s is kept fixed, and we are effectively integrating over t. So this unitarity cut and the t channel.
Sasha, I have a question. There is T of z, but T of z is equal to, there is also s in there, right?
Yeah, there is s. Yes, it depends on s.
So the actual, no, I mean the t is also is not just a function of.
Yeah, t depends on s. Sorry. Yes, you're right.
So does this change the analyticity structure also in the S channel now? I mean, it's a completely different story.
No, because the dependence on s is trivial. It's t is just s minus 4, it's 1 minus 0, whatever. So it's just a fixed number. So it's a triviality. Yes, if you start meddling with s, maybe you can worry, but we're doing this for fixed s.
Okay, I see.
And this formula, if you want to ask the condition for dropping the cuts, if your amplitude behaves like some power of t, which depends on s, and this is sometimes called the Regge intercept. So let's say your amplitude at infinity behaves like some power, then this formula, which was written by dropping the cuts, only valid for j larger than j naught of s. Now, so far this formula has been derived for integer spin, but what you find is if you look at this formula, is that in fact this formula is manifestly analytic in spin. Or in other words, if you take it from integer j's, you can apply Carlson theorem. So therefore, in fact, when we're talking about partial waves, then we should think about j being the complex number. So this is general, also one of the general topics of our discussions, that things become complex. Just from this formula, there are already nice things you can derive. For example, you can ask what happens with this formula as j becomes large. And what you find is, as j becomes large, this integral gets localized to this threshold, because these qj's decay with spin very quickly. And so there is a map. If you start with T of t, this is a low energy region. So this is low energy in one channel. You see that low energy in one channel is mapped to large spin in the other channel. So this is a kind of things which happen in relativistic theory where you have crossing. But okay, let me not go there.
Such a quick question. So the J0 there, so since we're assuming maximum analyticity, we can use Frossard bound to say it's infinity.
So yes, Frossard bound here does not apply because recall that S here, FGFS, it's a physical S. So S can be 10, 20, 30. Frossard bound doesn't say anything about.
Even assuming larger, because this T less than 4 and square was not related to analyticity, it was just a hard.
It was really, yeah, it was for T less than 4 and square, we have a bound. For T larger than 4 and square, in T, if you assume maximal elasticity, we have no idea.
Even if you assume maximal.
Even if you assume maximal elasticity, yes. And the reason is that your partial waves stop converging, and then. Okay. So yes. So now let me prove. Maybe this will be the last thing I want to talk about, but it's such a beautiful result. So, and again, it leads to another problem, which is very easy to state, but very hard to solve, and it was not really, hasn't been really solved convincingly. So now, after I introduce Frossard-Zhiboedov formula, we can prove something which is known as the Axe Theorem. It's Axe. Axe is the name of a person, and it's a theorem assuming this extended analyticity. This is one of the shortest theorems that I know of. It states like this. So in D larger than 2, D is a number of space-time dimensions. Scattering implies production. So what do I mean by scattering? Well, scattering is just a statement that, let's say we have a theory, we have particles, and we have an amplitude, which is 2 to 2. And this thing, which is this T of S and T, this is non-zero. This is, by definition, what I call scattering. What is production? Production is a statement that if you have 2, and you say you have 4, this is non-zero. So you have produced 2 particles. And so theorem says, in D larger than 2, if you have this, then you must have that. Now, D larger than 2 is important because if you consider D equal to number of space-time dimension being 2, then in fact there are counterexamples, and these are integrable theories. Integrable as matrices in 2 dimensions are theories where you have scattering, but you do not have production. However, the statement in D larger than 2, this is not possible. You could have asked, okay, you told us that we do not have an explicit example of an amplitude in this course. Maybe it's too complicated, but maybe there is an integrable theory in 4 dimensions, you just missed it. So this theorem tells us that no, we haven't missed anything, and in fact, integrability, there is no integrability, and at least in this sense, you will have a particle production. Now, there is a one-line physics proof of this fact, which is not really a proof, but it's a picture. So let me draw this picture. So you might think, okay, well, if I have such an amplitude, why don't I construct something like this? I take one amplitude, I will make it virtual, one leg, because this is 1 to, well, this was 2 to 2, but let me make one leg virtual. And here you go. So this is a process where two particles go, exchange one particle, and generate 4. Now, the problem with that is that, well, this is an S-metric theory, so it's only on-shell things exist. So there is no such a thing as virtual particle here in this thing. However, if you remember, we had a trick when we discussed, for example, electromagnetic form factor, is that if you start with a momentum space and you go to large impact parameter, what happens is in general that you start exploring, so here if you start with the physical kinematics, this particle is virtual because this momentum exchanged here, this q squared, it's negative. Whereas the mass shell condition for this particle is equal to q squared is equal to m squared. However, what happens is, we discussed this when we discussed electromagnetic form factor. When you start going to the large impact parameters, you start exploring the nearest non-analyticity in this variable. So in fact, if you take instead of a momentum and separate the things at very large distances, this particle goes on shell. And then you have this kind of diagram. Where this particle goes on shell. Again, the mechanism was the following. If you exchange a particle, something like this, when you do the Fourier transform, by going to you're going to impact parameter space, then you start deforming this contour, exploring the situation, because you see it effectively on the pole when q squared becomes m squared, and this is effectively sets this particle on shell. So the physics intuition tells us that, again, I'm still talking at the level of not completely rigorous, but qualitatively, if I give you scattering, it looks like there should be a particle production at large impact parameters always. Because if I go to large impact parameters, this particles goes on shell, and here I go, it gets 2 to 4. So this is a very intuitive argument. And yeah, and you can ask, okay, well, how do you know that there is another wrinkle here? How do you know that this diagram is not cancelled by something else? Okay, maybe there is some other diagram. Maybe exchange 3 particles here in the same way. But note that in the impact parameter space, each particle costs you a Yukawa potential, which decays exponentially. So you expect that at large enough impact parameters, these diagrams always decouple. You're just dominated by that, and here you go. It's going to be 0. So what Axe theorem does, it makes this this intuition precise. So this was the physics argument, but we can now do the math argument. So the math argument is the following. Remember at some point we wrote elastic unitarity for partial waves. Now let's assume the argument of Axe goes like this. Assume that there is scattering and no production. well, then elastic unitarity holds for any energies. Because remember, elastic unitarity was unitarity in the absence of particle production. And elastic unitarity takes the following form. Before we wrote it as an imaginary part of F. Now I'm writing it a little bit differently, explicitly taking this imaginary part here, the difference along the cut. And here we have d minus p over 2. So now, before, when this is elastic unitarity. Before we remember when we studied this equation, we studied it only for j equal integer, but we just learned that j in fact complex, and so this equation is valid for j complex. And in fact, there is another equation which is equivalent to that. The equivalence is established by the Froissart-Gilbert formula, which is known as the Mangosteen Equation. And the Mangosteen Equation takes the following form. Rho S of t, which is defined as a disk S, disk t of t, so it's a double discontinuity of the amplitude before, is equal to the, I will write it schematically, very schematically, because we don't have time for details. So some lower limit. With some factor, it's in the notes. What's important is that you have some discontinuity of t. You have this sign. Here you have some kernel. So what is this equation? Well, if you take this equation, you integrate it against the QJ polynomial, what you get on the left-hand side, you get the Froissart-Gilbert formula for the disk, by definition, because remember that Froissart-Gilbert formula was relating F to the disk T, and now we take the disk S, which is precisely this, and we integrate again QJ. So this gives us the left-hand side of the Froissart-Gilbert. And the right-hand side, it's a miracle that if you integrate against QJ this kernel, it gives you a product of two QJs, and this becomes this, and this becomes that. So these are equivalent things. But if these are equivalent things, why do I talk about them? And again, this is one instance where I hope again it becomes clear how the game goes. I just told you that, okay, we had this equation, and we just learned that, in fact, we have it for complex spins. However, you might think, okay, this equation is nice, but how do I implement crossing on this equation? For example, let's say I want to check crossing. And this equation, it's not clear how you check crossing. However, if you look at this quantity, this is a double disk of T, and this is crossing symmetric. In fact, this rho of S and T rho of S and T has to be equal to rho of T and S, which is just follows from T of ST equal to T of TS, and you take the double disk, which is a crossing symmetric operation. And now, here's a proof of Axe theorem. So you start with S and T. And if you look at the this Mangosteen equation, you can see just from the structure of the kernel and from the analytic structure of the amplitudes. I mean, it's not clear. I haven't quite explained that, but that this function rho of S and T can only have support here. So this rho S of T is non-zero here, and this is some Landau curve, which is explicitly known. So it is non-zero here, and it is 0 here. Here it is 0. So this is a consequence of elastic unitarity continued at spin or Mangosteen equation, which is the same things. Now, you can ask, well, when rho is non-zero, is it sign definite or not, for example? And what you find is that we don't know in general, but there is a region, say somewhere here, where you find that if there is scattering, rho is positive. How do you see it? You just plug, as usual, as we always do, you just plug partial wave expansion here. You have imaginary part of S. If scattering is non-zero, this is non-zero, and then the miracle of Mangosteen equation is such that this kernel is sign definite, so you get that rho is positive. So this is the picture that we get, assuming no scattering, and assuming that there is, say, no production. So what does production mean? If there is a production, then I have to stop somewhere. When this equation, which was elastic unitarity, remember, originally we wrote it for S, say, between 4m squared and 9m squared, if there is production. But if there is no production, you just go ahead. You can apply it for any S. And so now this equation is fine. This is the structure that we got. But now let's combine it with crossing. So, well, if we have crossing, this picture has to be crossing symmetric. So we have to make it crossing symmetric. And if you make this picture crossing symmetric, you get this kind of kernel, and you get this region where you conclude that rho is non-zero from crossing. And now you see we are done. We arrived at the contradiction. We said that rho is 0 here, and here we say that rho is non-zero. And the contradiction came from crossing and from applying this equation here, and this assumes no production. What happens in the physical theory, as you tend to approach here, you tend to get a contradiction, but in fact, when the production starts, this equation stops holding. So it only holds here if there is a particle production, and you do not have any contradiction. So this is a proof of the Axe Theorem. And again, here there is this, again, nice interplay of positivity, crossing. This time, before I was applying crossing to the amplitude. To prove the Axe Theorem, you apply crossing to this double discontinuity. So, I think let me end this lecture course with a question which well, maybe it's a little bit sounds silly, but still. So the actual question which we are trying to understand, I think, and so I haven't told you, people are trying to cook up some other ways to probe this non-perturbative amplitude, but the question is really, what is a non-perturbative scattering amplitude? And by this I mean not maybe a philosophical question, but practically. Say we know that when we remove here this non-part, we have a great understanding. We have Feynman diagrams. We have a good grasp over what it is. And in fact, in the experiment, sometimes the Feynman diagrams describe things very well. So we clearly see that we understand something, but somehow when we try to promote this to something non-perturbative, it's not fully clear what do we have to add. Clearly, non-perturbative scattering amplitude, it is the only answer I think that we have today. Up to today is that it's an object that satisfies non-perturbative unitarity, that satisfies crossing, which satisfies analyticity, and that's it. And now the question is really how far we can go combining what we already know and this non-perturbative understanding, non-perturbative look of the scattering amplitude. It's an open question, but I think I try to update you on where we are now looking at it. Thank you very much for listening.